in Taiwan and also in US. And we are really excited tonight. We have another speaker joining us for this data analytics colloquium. And we have Dr. Matthew Lebo from the University of Western Ontario. And Dr. Lebo will give a talk. The talk's title, Beyond the Univariate Question, Drawing Inferences About Long-Run relationships given uncertain univariate dynamics. Allow me to give a little more detail to introduce Dr. Lebo. And Dr. Lebo currently is the chairperson and also the professor at the Political Science Department at University of Western Ontario and Canada. And his research focus is on national level and politics in the United States, political parties in Congress, the presidency, and the elections. Then his work include the strategic decisions political parties must make to balance electoral and legislative goals. He also studies research methodology and time series analysis, and his additional interest in British politics and election forecasting and Scottish independence also. And a little bit more information about Dr. Lebo, and he has been the chairperson also at the Political Science Department in the State University of New York, Stony Brook. And he's most well known of his time series work published in political analysis, HAPS in many journals, and he's also a political methodologist. And I have some personal note about him because he's also a student of Dr. Harold Clark, and he we shared some time together at the University of North Texas, and he came in a little late, but his work is much more remarkable. And particularly his work on fractional time series and call it FEMA. And he spent some time in Harvard as a postdoc, then went on to Stony Brook and a few places. And he's really prolific and one of the most prolific scholars that I know. So I published extensively and on British election, American elections, and particularly in political methods. Without further ado, allow me to bring Dr. Lebo to come to the stage. And Matthew, please. Thank you.
Okay, thank you. Thanks, Carl. And yes, Carl and I go back a long way to Denton, Texas in the 1990s.
Yes.
Students of Harold Clark.
People know how old I am now.
So it's a real treat to present this to the audience at UTD as well as NCHU. All right, so I can see my slides now. So I'm just going to tell everybody I've had a bad cold this week, and so I may stop for a little bit of tea or a cough drop at some point, or to cough. But I think I'll be okay. So this this project comes from joint work with Susie Linn, who's at Penn State University, and Clay Webb, who's at the University of Kansas. And the three of us have been working together for about 6 years on 2 papers that are part of this project. And now we have a book that's almost done that will be forthcoming that goes through these methods as well. Okay, next slide, please.
Is it okay? Right. Maybe. Does it work? Do you see the new page?
I can see the next one. Okay. So today I'm going to talk about the motivation for today, and then I'll talk about different equilibrium types, and then I'll talk about this bounds method that we call the WLL. That's Webb, Linn, and Lebo bounds methods. And then I'll go through 2 or 3 examples quickly if we have time. If you have a question, yes, you can post it there or speak up. I may not spot it in the chat window, but if I do, I'll try and answer it as I go. Okay, next slide. So usually when we're analyzing time series, we start with the question of, are our time series stationary or non-stationary? Usually this is the very first step in Harold Clark's week 1 of Intro to Time Series. You would learn about stationary versus non-stationary data. So stationary means that a time series, a variable measured over time, has a constant mean, a constant variance, and a constant covariance, so that it is always reverting back to these things, and the expected value of the mean, the variance, covariance, these are all constant across time. So any chunk of the time series will have the same mean, the same expected mean. Okay, next, please. So a stationary series always reverts back to its mean and does so pretty quickly. But there are time series that are not mean reverting. We call these non-stationary time series. There's a whole bunch of different names: non-stationary, or unit roots, or integrated, or I1, all mean the same thing, roughly speaking. So if our time series YT, something's happened there.
Sorry.
That's okay.
And I'm sharing the screen now. Okay.
There we go. So if our time series YT is equal to what y was at t minus 1 plus some random error, then we call this a random walk process. So we can move the yt minus 1 over from the right-hand side to the left-hand side. You can see that the change from y at time t to y at t minus 1 is equal to some random process u. So a random walk model is this equation here: yt equals alpha 0 plus alpha 1 at yt minus 1, when alpha 1 equals 1. That's where we get the term unit root, right? When alpha 1 equals 1, we call that the unit root. So that's a non-stationary time series. That means that it will accumulate over time, or it has perfect memory, so that its value at any one time period is the sum of all the changes that have occurred in U over its entire history. A white noise process, though, is one that has no memory at all, where alpha 0 equals 0, alpha 1 equals 0, and this, so that the equation there, just yt, the second from the bottom there, just becomes yt equals ut, and that's just a well-behaved error term. Okay, next, please. So here are just two examples. On the left-hand side, that's a stationary time series. It's always reverting back to its mean, has constant variance, constant covariances. You could take two series like that, run a regression, and you would find a significant relationship, 1 in 20 times at the 0.5 level. There's not a spurious regression problem there. On the right-hand side, though, is what is a random walk series, where that series is the accumulation of those short-term shocks over the entire history of the series. And so a unit root series like that can just meander for a long period of time. It may never go back to its original mean. We don't think about it really having a mean at all that's a meaningful mean. It wanders by itself. Okay, next, please. So the problem with non-stationary series is that when we have regressions between two non-stationary series, we are very likely to find relationships between them, even when they have nothing to do with each other. So this actually goes back before Granger and Newbold. There's a paper by Ewell in 1926. Why do we sometimes get nonsense relationships between time series? And I don't know how Ewell in 1926 was simulating time series, but he was, and found this pattern. Granger and Newbold found it as well, and found, okay, if you have two of those non-stationary series that have nothing to do with each other, what's the chances of finding a relationship between them? It's about 75%. Right? Two series that are both going upwards over time, even if they have nothing to do with each other, you'll think, well, they're going upwards over time, then there's a significant relationship with them. If one is going up and one is going down, you'll probably conclude, well, there's a significant negative relationship between them. But the fact that they are increasing their variance over time and meandering away from their original time point, their original spot, means you're likely to find a relationship there. So there's all sorts of spurious relationships. And this is, the real danger of dealing with time series data. You have to be very careful to use appropriate methods, or you might make inferences that are incorrect and tout relationships that are actually there. Okay, next, please. With stationary series, you don't get these false positives. So this tells us that it's really important in traditional time series analysis to know what kind of time series you have. And so the first step is usually to go through extensive diagnostics of every variable that you're dealing with. And so there's dozens and dozens of tests that you would subject each of your variables to. And you try to figure out, is it stationary, is it non-stationary? There's fractional integration, which is in between. And these tests can be really difficult. And when the time series are short, especially, you'll get contradictory results. And sometimes you just cannot come to a firm conclusion over whether a time series is stationary or non-stationary. And when a time series has got about 50, 60 data points, like lots of yearly time series of post-war yearly time series, it's just it's sometimes impossible to know, and tests will contradict each other. Okay, next. All right, so now I want to talk about equilibria. So an equilibrium means that there is no inherent tendency to change. When there's a disequilibrium, it means a situation that is not an equilibrium and characterizes a state that contains the seeds of its own destruction. That's a quote from Banerjee, which is that's an all-time book on co-integration analysis. That was always on Harold Clark's desk, I remember.
Yeah.
So an equilibrium is a place to which a time series naturally tends, right? So we want to think about that. It can mean different things depending on the nature of the time series. An equilibrium means different things. So next slide, please. So for a stationary time series that has a stable mean and a stable variance and constant variance, its equilibrium is its mean. So if it's out of equilibrium, that means it's away from its mean and it's on its way back to its mean. If it jumps above, it's going to rush back down to its mean. So that long-term, that stable long-run mean pulls the series back towards it whenever the time series deviates from that mean. Sometimes this happens pretty quickly. It can take a little bit longer. There's things like autoregressive processes that have, longer memory, but eventually everything reverts back to the mean. Next, please. Okay, but a non-stationary series doesn't have a stable mean or stable variance or constant variance. So it has no equilibrium on its own. You think about that random walk that was walking, wherever it was going to go. What was the equilibrium that was seeking? Well, it didn't have a mean that it was seeking. It is possible, though, that two non-stationary series could be in equilibrium with each other. That a series that is a unit root or non-stationary might seek to be in an equilibrium relationship with another non-stationary series. Okay, the next one's good. So I want to describe three types of long-run equilibria. First, a stationary series has an equilibrium that is its mean. And a stationary series can seek that mean in two different ways. The first we'll call an unconditional stationary equilibrium, which means that the mean-seeking behavior of that variable is not conditional on any x, right? It's not predicted by any x, it's just y is reverting back to that mean. If the mean is conditioned on some x, then we call that a conditional stationary equilibrium. So a mean stationary series can still be predicted by an x, and it reverts back to some mean that is predicted by the x. And so you can have a relationship between x and y, between a stationary x and a stationary y. For a unit root series, though, there's no mean value, but if they both contain unit roots, and then their combination creates a mean reverting series, we call those two series co-integrated. So co-integration is about when two time series that are unit roots that wander off, that they are tethered together. That's a co-integrating equilibrium. Okay, next slide, please. Okay, I guess there's
You can move too fast.
It's okay, you can keep it there, but I guess the metaphor that is so often used to talk about two co-integrated series is the drunk and her dog, right? If anybody's, there's a famous paper, well, the first paper was called A Drunkard's Walk, that was about explaining a random walk. And then years later, someone came along and explained A Drunk and Her Dog. So the idea is that a drunk may go out for a walk that is quite random. You don't know where they're going to go, and where they wind up is the sum of all of their steps. But they could be out for a walk with their dog, who is on a leash. And the dog and the person are somehow, they're tethered together. And nobody knows where they're going to go, but they're going there together, and they don't get too far away from each other. And we can think of that in a few different ways. We could think of it when we have just y is an endogenous variable and x is exogenous. We think about the dog returning back to the person. But we can also think of that in sort of a multi-equation framework, when the person and the dog go back to each other. In our book, we go through various types of dogs, and what that means. The relative size of the human and the dog tells you something about who's moving. So if x and y are co-integrated, then for this to, there's really strict criteria to find co-integration. Both x and y have to be I1 series, so that each contains a unit root, and each one can be made stationary by taking first differences. So this is a really important step, right? When y is a function of y at t minus 1, then we can also create that delta y, the change in y from y at t to y at t minus 1, and that will be a well-behaved stationary error. So if y is a unit root and x is a unit root, we can create delta y and delta x, and those two series are stationary. So despite the fact that both x and y are non-stationary, a linear combination of the two of them can be stationary. So think about that. What is stationary between the drunk and the dog is the length of the leash, right? It doesn't, that always reverts back to 0. The distance between the dog and the leash, this distance between the dog and the human always reverts back to them being together. Okay, so we can do that in a few ways. Yes, Carl.
Yeah. Good. Allow me to interject. I think when now we are coming to a little bit technical detail now, and maybe to those students, including mine, and they may not have taken any time series courses at all. And please feel free to ask any question, and particularly about this stationarity, first differences. And maybe I can ask a quick question, and maybe now on behalf of the students, from the students' perspective. Now, what if you, for example, you showed before that YT is somewhat related to YT minus 1, and which is like a incremental process. And I think Peter should know this. We do the budget, and I think Dr. Clark's class always uses like a budget, and this year's budget is kind of related to last year's budget. Take some increment, or maybe something get cut a little bit, but it's still related to last year's budget. But what if, can you give an example, like the two YT and YT minus 1 are totally independent?
Where YT and YT minus 1 are totally independent?
Yes.
Not really.
Could be.
A completely stationary political time series
Mm-hmm.
is very hard to think of.
Mm-hmm.
Things that are different are much closer. So, you know, a unit root series like the stock market is close to a unit root process, and tomorrow morning it will open up what it closed at today, and it's the sum of all its daily changes. But the daily change in the stock market is pretty stationary. It goes up, it goes down, it goes up, it goes down. There's some memory to that. You know, there's rallies that last for days or something like that, but that's much more of a stationary series.
What if there are some like event data? So, for example, there was a conflict, there was a riot yesterday, but today there's no riot at all. Yeah. Would they consider like a not? Yeah.
There are many different ways of compiling time series, and event data often has memory. As you know, depending on the level of aggregation. If you aggregate things by days, then what happens today has something to do with what happened in the previous days. If you go up to higher levels of aggregation, maybe there's less memory there. But yeah, there's many different ways that we create political time series, and the testing problem for deciding whether your data are unit roots or not is usually about how much data you have. When you get to 200, 300 observations, then you can have a decent chance of really diagnosing sort of the data generating process. But when it's short, no matter how it comes from, even when you have a time series where you know how it's created, it may not test in the way that you think it does. So an example that I use is the liberalism of the Supreme Court in the United States is measured by some score of the median justice in the Supreme Court. And that's done on a yearly basis. So this year there's 9 justices. There's a new justice. Next year, the median justice will be the same median justice, and their ideology won't change. But so if I get 50 or 60 observations of that, it may still be very, very difficult to test, is that a stationary series or a non-stationary series? So where I'm leading you is to a method that doesn't require you to know.
All right, great. And I think we can bring some more applications. If you have any questions about in your field, like public administration, public policy, or other disciplines, please bring up the questions. Thank you. Yeah. All right. And just want to make sure that the students can ask any discipline-specific questions too. All right. Thank you.
Sure.
Please go ahead. Thank you. Yeah.
Okay. Next slide, please.
Yeah.
So co-integration then is a very close relationship. Series that are integrated can be combined to create a series that is stationary. And so if so, we call that a co-integrating equilibrium relationship. Any distance that grows between them is short-lived, like the drunk and the dog. Okay, next slide, please. So this is a famous example. This is Stock and Watson's, this is from a macroeconomics textbook. And this is Stock and Watson's example from co-integration. These are 3-month and 1-year treasury bill rates in the United States from, I don't know if that's 50 years worth of data. And these two bank rates are set, I guess, I don't really know anything about how treasury bill rates are set, but I imagine they're set by the same people, and they're always very close together. Okay, so those are 2 unit root series. Each of them separately are unit roots, but if you'll see, the deviation between them never gets too big. If one series gets away from the other one, they always come back towards each other, right? They are definitely tethered together. So this is a common example from economics, and this is what they call an error correction rate of 52% means that when a gap opens up between these two series, that 52% of that gap disappears in the following period. So they are very closely tethered together. Now, the next slide gives you an example from political science. And in political science, our data is so much messier and usually so much shorter. And so this is data from a paper by Kelly and Enns that was in the AJPS in 2011, where by not being careful with their inferences, they looked at these three series and concluded that those had an even higher error correction rate, that those three series were tethered together really carefully. I'm showing you this just to give you a sense of how easy it is to make inferential mistakes if we misclassify the kind of time series that we have when we go through standard models that political scientists use. Okay, so I'll go through the various models that led to some wrong conclusions with that data, and then I'll pull that up at the end and we'll use that as an example. Okay, so here, the top two panels are the top left panel is 2 unit root series that are not related to each other. Those two are randomly generated. And when we run a correlation between them, it's a positive correlation. It's 0.256, just occurs randomly. If we ran just a regression of one on the other, we'd find that statistically significant. When we go through the more rigorous process of testing for co-integration, we find that the residuals of a regression of one on the other in the top left is still non-stationary. And so the top right is the residuals from that regression. In the bottom left, you have 2 series that are created to be co-integrated with each other. They have a much higher correlation. And when you regress one on the other, you get the bottom right. You get very stationary errors. So the bottom right is a mean reverting process. By combining two random walk series, we've created a series that is stationary. Okay. All right, next I want to talk too about something called equation balance. And equation balance is something that econometricians talked a lot about for a long period of time. Political scientists didn't pay too much attention to it. And what we mean by this is that the variables that are on the right-hand side and on the left-hand side of the equation should be integrated of the same order. We do not want to be regressing a random walk time series on a stationary time series, right? It doesn't actually make sense to look for a relationship between one series that wanders off forever and another series that is stationary. They shouldn't have a long-run relationship with each other. So we think about a lot of where political scientists come at equation balances in the pre-whitening tradition. So pre-whitening is the idea of, I'm going to go into all of my data, I'm going to see which is stationary and which is non-stationary, and then I'm going to transform any of my series so that I can make them all stationary and make them all the same. And that's usually done by differencing. So if I started off and I found that y was stationary and x was non-stationary, then I would have to difference my x so that I could have 2 stationary series and have equation balance. Okay, next. So Banerjee has this quote: when the investigator is attempting to explain an I0 variable by a variable integrated of a higher order, this will eventually fail, as the 2 variables must diverge by ever larger amounts. And Granger says one of the basic properties of a model is that it should balance. In fact, every equation in the system should balance. So I'll demonstrate that a little bit with this graph. So here, the blue line is a white noise series, and the red line is a random walk. There shouldn't be a long-run relationship between those 2 series, right? And if I try and run a regression, try and explain that, it should break down. The regression should break down. My theory should break down. I shouldn't be able to link those 2 things theoretically. Okay, next. All right, so now let's talk about different models that we use for time series data. And these are three mathematically equivalent models. So the first, equation 1 there, is the autoregressive distributed lag model. And that's y at t equals alpha 0 plus lagged y, that's y at t minus 1, plus x at t and x at t minus 1. The ADL is usually used for stationary data, right? You can see that we would have a worry about spurious regressions there, because if the series were unit roots, we wouldn't want to use that model. Spurious regression problem. The second equation, 2, is what's called the general error correction model. And this is a model that we use to look for co-integration. So this model is much easier to explain when the data are unit roots, like those 2 treasury bill rates in that example. So delta y, that's the stationary version of y, is predicted by the gap between the level of y and the level of x. So when y and x in combination are stationary with each other, right? The deviation of y and x should be stationary. And so this is stationary, and this piece is stationary, and this piece is stationary. And this might be a worry if I include this. So the general error correction model is used an awful lot by political scientists. And this equation 3 is the one that's used all the time. This equation, delta y, is predicted by alpha 1 star times lagged y plus beta 0 x delta x plus beta 1 x at t minus 1. So you have on the right-hand side delta x, and you have y and x. This is just a transformation of this here. So if y and x are really tethered together, then these in combination are stationary. So the inferences that we would make from the GECM or from the Bardston model are a little complicated, but they're straightforward and well understood with unit root data. But when we get away from unit root data, then we get into shaky territory. Okay, next, please. So this is really, really simple. Just to estimate this in stata is d dot y, l dot y, d dot x, l dot x. That's the whole thing.
Mm-hmm.
And if the data really are unit roots, then alpha 1 star is a test of co-integration, and it's a test of error correction. And beta 1 star is a test of whether or not x and y are in a long-run relationship. Okay, next. So where political scientists really got into the general error correction model was following a 2008 article by DeBoeuf and Keel. DeBoeuf is Susie Linn, and Luke Keel wrote this article in 2008. And they demonstrated how the ADL and the GCM were mathematically equivalent to each other. And their article did confuse a lot of people. So in particular, there's one quote: alternately, as the ECM is useful for stationary and integrated data alike, analysts need not enter debates about unit roots and co-integration to discuss long-run equilibria and rates of re-equilibration. So what a lot of people did is they just pulled out this model, they pulled out that little bit of stata code, they ran their time series data through it, and they interpreted the results that they got as though they were interpreting the model with non-stationary data, as though it was a co-integration test. But the inferences are drastically different if the data are not unit roots. Okay, next. So we get a lot of people using that model, That paper's been cited well over 1,000 times, and lots of articles, especially in American politics, that model's been used an awful lot. Yearly data on American institutions with 50 or 60 years of data. We see that a lot. So there's an exchange that in political analysis where I wrote an article with a former student, Taylor Grant, where we said even though the model it's treated as though it's perfectly flexible, there's real problems of interpretation if you're not careful. And Keel, Linn, and Webb, talking about their taking time seriously in 2008, said we did not suggest that the GCM can be used for any and all time series data. And so they in this exchange in political analysis, they were careful to explain exactly what they meant that you could do and couldn't do. All right, next. So in part, problems occur when people rely too much on alpha 1 star. Okay, so I want you to, if you can, try and think about what alpha 1 star should be if the data are just white noise. So if the data is really white noise, then what that tells you, then what I'm predicting is how Y changes based on where Y was in the previous period. So what that actually would do is, if it's really white noise, then as soon as if Y at t minus 1 was above the mean, then the change at Y at t would be to go back to the mean. And if Y was below the mean, the change would be to go up to the mean. Mm-hmm. So if your data are actually stationary, alpha 1 star should be minus 1. If you think that if you interpret that in the exact same way as you would when the same way you would with looking for co-integration, you would think -1 is a long way from 0. That's a very, very close relationship. Okay, so this is where the big misinterpretations come from, is first relying so much on alpha 1 star. And finding a significant alpha 1 star then could mean that there's co-integration, or it might not. It could just mean that Y is stationary. It could mean that there's error correction going on there, or it might just mean that Y is stationary. The correct interpretation of alpha 1 star depends on the univariate properties of the series. Mm-hmm. Mm-hmm. Okay, next. All right, so we have methods that allow us to look for long-run relationships when we're sure that the data are non-stationary. Engel-Granger or the GCM works just fine. And there is a method that we can use if the dependent variable has a unit root, but we're unsure about the independent variables. This is a method by Pesseran, Shin, and Smith that's been cited about 17,000 times. Wow. It keeps going up year by year. It's only 20 years old and it goes up every year. It's now really a go-to method in econometrics. Okay, next. So we know how to adapt these models when data are stationary. We know how to do different things like pre-whitening and look for fractionally integrated time series and fractional co-integration. Next. But what we don't have is a method that allows for the researcher to be uncertain with respect to all of the variables in the model. So what happens if we don't know about any of the variables, if none of the variables are really cooperate with us when we try to test them? This happens a lot. You may have, 2-3 time series, and you want to know the relationship between them. And they're too short, and you get contradictory results from stationarity tests and Dickey-Fuller tests and that sort of thing. So PSS would allow this if your independent variables are unknown, but the dependent variable has to be a unit root. So what we need is a model that allows uncertainty with everything. Okay, next.
Yeah. Allow me to ask this question. Can we can you interpret a little bit more about PSS using a lot of parameters? So that means not just one per IV, or could be multiple per IV.
There's lots of lags. The PSS test
Oh yeah.
involves lags for
so that means
there's
so
other
the right hand
advantages.
side could be
yeah. So for economists who usually have a lot more data than political scientists, they manage. But political scientists can quickly run out of degrees of freedom that way. And there's other advantages to what I'll show you as well.
Yeah, and the series are longer too. Yeah, usually.
Yeah.
Yeah.
So, so the method that I'm going to show you comes from a paper with Webb and Linn. There's actually two papers. So the HAPS is an easier read, and then we go through the derivations in the political analysis article in 2019. And the challenge that is, how should we analyze long-run relationships when we're uncertain whether the data are stationary or have unit roots? So this is sort of just dealing with the consequences of imbalance. We began by looking at PSS and saw the limitations there, because PSS absolutely required that the dependent variable is non-stationary. But if you can't figure out what your independent variables are, maybe you can't figure out what your dependent variable is either. So we have a method now that doesn't require you to know about any of them. Okay, next, please. So what we use are called critical value bounds for hypothesis tests. We find one key parameter of interest, the long run multiplier, and then we create critical value bounds for hypothesis testing that take account of the inherent uncertainty of trying to find the dynamic properties of the data and make inferences about long run relationships. So this is quite different than from the PSS test, which looks only at co-integration and can only happen if Y is a unit root. Okay, next. So lots of times we're uncertain about the univariate dynamics, and we want to know whether there's a valid long-run relationship. It could be a conditional stationary equilibrium, or it could be a co-integrating equilibrium that exists between Y and X. So what the bounds procedure does for a regression that has Y and X, and then a regression that has Y and 2 X's, and Y and 3 X's, and 4 X's, and 5 X's, we simulate all different combinations, every possible combination of what the stationarity properties could be for those time series. And based on that, we can come up with different scenarios where we know what the lowest the critical value could be, and we know the highest the critical value could be for the long run multiplier. So when we mix different stationary and non-stationary series, we have different kinds of different critical value bounds. And so we derive the limiting distributions for two polar cases that establish a bounds test for the long run multiplier. So there's a lower bound, and this is a combination of, it's not that everything is stationary, everything is unit roots. It's like the dependent variable is stationary, and or dependent variable is a unit root, and one of the independent variables is a unit root, and the other ones are stationary, something like that. We have a lower bound. Okay, next slide. And we have an upper bound. And we calculate a test statistic. And if our test statistic is below the lower bound, then we know no matter what the true data generating processes might be for those variables, we would not be able to reject the null hypothesis. And so being below the lower bound, we fail to reject the null hypothesis. If we are above the upper bound, then we know that no matter what the combination of stationary and non-stationarity is between the Y and the X's, that we are above the upper bound. And so above the upper bound, we can safely reject the null hypothesis. And if our critical value is in between those bounds, it's inconclusive. Next slide. So we have two conclusive possibilities, and then the next slide is just going to say inconclusive in between. So this is perhaps a little unsatisfying. You know, there's a chance that you would, we're used to having a hypothesis test, and you run your hypothesis test, and you either reject the null hypothesis or you fail to reject the null hypothesis. And now we have this middle region where we're unsure. And really our approach is that researchers need to be transparent. If you don't know the true nature of your time series, then it's possible that you're not going to be able to make a conclusive conclusion about whether there's a long-run relationship between them. Okay, next slide. Okay, so the LRM, we can skip this slide. This is a little more complicated. There's data manipulation to do this. The Bewley is a version of the GCM. The long run, let's see the next slide. So here, the null hypothesis is about lambda. So lambda is the long run multiplier, which is beta 1 star divided by the negative of alpha 1 star. So those two coefficients that came out of the GCM, and I test whether it equals 0. And that tells me whether or not there's a long run relationship between X and Y. If I fail to reject the null, it means that I can't conclude that there's a long run relationship, regardless of whether the data are unit root or stationary processes. If I reject the null, it means inferring that a long run relationship exists between X and Y. And this is the test that we want. Okay, so I'm not going to rely on.
Can you refresh? Yeah.
Go ahead.
Can you refresh our memory? Yeah. Can you refresh our memory about alpha and beta? I think one is associated with the leg Y. One is associated with leg X, right? X and leg X's.
Exactly. Exactly. Yeah. So beta 1 star is the coefficient on the lag of X, and the alpha 1 star is the coefficient on the lag of Y.
The lag of Y. Yeah. Yeah.
Okay. Next.
Okay. Okay. Good.
All right, so when we're evaluating lambda, we aren't forced to diagnose our time series. If I reject the null hypothesis that alpha 1 star equals 0, that's not a useful test, right? That would imply that Y is co-integrated with the vector of X, but it wouldn't tell us which X contributes to a co-integrating relationship. Well, but when I calculate, I can calculate then a different lambda for each one of my independent variables. So I can test the long run relationship for each X separately, which is a value we have over the PSS test. And it does make it impossible. When I find a relationship, I can't say what it is. Right? When I find that there's a long run relationship, I'm not going to be sure whether it's a co-integrating equilibrium or a conditional stationary equilibrium, because I haven't decided whether my data are stationary or not. But again, if we can't diagnose our series at the beginning, then we want to be very careful about what we conclude with the relationships between.
So on the point 2 and 4 here, do you mean that could be certain period of X could have different contribution to the relationship, and certain period, for example, could be the wartime, or could be the baby boomer period, and if you have a long run series, there's spanning multiple decades, for example. So do you refer to different period that could be contributed to different co-integrating relationships?
That's not how I'm thinking about it here. I'm thinking about how different independent variables might have different effects. So x1, x2, x3, where x1 might be an economic measure and x2 might be a political measure and that sort of thing. So I want to investigate.
Okay, different right-hand side variables. Sorry. Okay, good. Yeah.
Okay. All right, next.
Yeah.
So with the GCM, the long run multiplier, lambda is beta 1 star divided by alpha 1 star. And that gives us the total effect of a unit change in x on y. So a long run relationship exists if and only if lambda is defined and is non-zero. That is, both the numerator and the denominator are non-zero. Next. If y and x are both unit roots, they may or may not be co-integrated. If they are co-integrated, that means that alpha 1 star does not equal 0, which can only occur if y is linked to x. So lambda then is defined in non-zero. And then depending on beta, that would tell me whether or not I had a significant long-run relationship. If x and y are not co-integrated, then alpha 1 star equals 0. There's no link to x in the long run, and lambda would not be defined.
Because the denominator cannot be 0.
Right. Okay. So if the data are stationary, then alpha 1 star can't be 0 by definition because of mean reversion. So lambda will be defined. But lambda will only be non-zero if y is linked to x, which implies that the numerator is also non-zero, and then there's a long-run stationary relationship. If y is not related to x in the long run, then lambda equals 0. Okay. So these calculations come from the GCM, but you can do this, you can calculate a long-run multiplier also from an autoregressive distributed lag model. So this is an ADL, and lambda is beta 0 plus beta 1 divided by 1 minus alpha 1. Okay, it's just a rearrangement of the same parameters for two different models. Okay.
Okay. Oh, okay.
So for each long run multiplier, I'm testing for the long run relationship between that x and a y, and I'm doing that regardless of the properties of the data. If I fail to reject the null, it means that I can't conclude that a long run relationship exists, regardless of whether the data are unit roots or stationary processes. Rejecting the null means we can infer a long run equilibrium relationship between x and y, and this is the test that we want. Okay, next. So calculating the LRM is easy. The standard error is not so easy. And so we need a fix, and that involves this estimation of the Bewley regression on the next slide. And this is a bit messy. This is a transformation of the GCM that involves instrumental variables. And in this case, it's psi 0, not psi 1, is the LRM. And in the AJPS article, that's a typo. That's a horrible typo that we made. That wasn't pointed out until after we published it. We named the wrong parameter. So the Bewley transformation allows us to calculate the LRM and its standard error directly with ordinary least squares using instrumental variables approach. And in our footnote, we explain all those transformation details. Next. So the distribution of the LRM t-statistic and the critical values for the hypothesis test on the LRM depend on the univariate characteristics of the variables in the model and the deterministic features of the DGP for y, the number of independent variables, and the sample size. And so we use all that information and run a lot of simulations and get a table of critical value bounds that's next. So this is table 2. This is what we call the money table. These are the value bounds that you would pull out to test your long run multiplier and see if it's statistically significant. So what we have is 3 levels of significance. Alpha equals 0.01, 0.05, 0.10. And we have different sample sizes, 25, 50, 75, 150, 500, and 1,000. And 1, 2, 3, 4, 5 independent variables. And so we run all these simulations with all the different possible combinations of time series and get critical value bounds. So if you look down at the 0.5 level with 1 independent variable, t equals 75, you see 1.06 to 3.73. So that means if my critical value is below 1.06, then I'm comfortable saying we failed to reject the null hypothesis. If my critical value is above 3.73, then I'm comfortable saying that we reject the null hypothesis. And if it's in between, I say we don't know. Okay, so this is the table that you want to have handy when you try this method. And you'll see that the number of independent variables doesn't make much difference. Right?
Yeah.
Okay, next.
Quick question. But the zone between the lower bound and upper bound is more of a function or a function of the critical value of our alpha value, 0.01, 0.05. And you can see 0.01, for example, if you have a very small sample, the gap is like 4 to 5, 1.8 versus 6.28. We have one variable only. So that is quite a big zone and a gray area. So that makes it prone, makes it more prone to make the conclusion, even that is actually inconclusive, but you do that, ignore this zone, that means the inference will be drawn incorrectly. So very much sensitive to alpha value and also the sample size, and more the alpha value first, right?
Yeah. Yeah, I mean, to find a long run relationship at the 0.1 level with 25 data points, not knowing the properties of your time series, you want very, very good evidence. And so that's a very high critical value, 6.28.
Yeah. Yeah. Important. Yeah.
Okay. So you don't need to know whether a series is stationary or unit root. You don't need to know if it has a random walk with drift, or random walk with trend and drift, which are other types of time series that I didn't get into. The bounds allow analysts to focus on the theoretical questions and the existence of long-run relationships. Okay, next. So this is just some code here. If you have access to these slides, you might want to try just adapting this code to your own data. This is very easy to make a mistake. It's quite tedious, but this is the instrumental variable regression that will give you standard errors as well as your long run multipliers. And you get separate. This is for 3 independent variables. You get separate long run multipliers for the 3 independent variables, and then you can compare those with the table 2 that we just went over. If the test is below the lower bound, fail to reject. Above the upper bound, reject, and in between, it's inconclusive. All right, next. So here's some British data for Carl. This is British data, Labour vote intention, Labour PM approval, Leader of Opposition approval from 1997 to 2010. So this is New Labour's time in government. And see the next slide. We want to see, are there long run relationships between these? So here I'm trying to predict, this is Maury's vote intention for Labour. And is that predicted by government leader satisfaction? That's prime ministerial approval. Okay, and so the t statistic that I'm interested in here is the 7.68. There's more output. I'm going to show you more of this model in a second, but that's in the graph of the data that I just had up for a second there. You see there's a close relationship, and this method is capable of rejecting the null hypothesis when there is a close relationship. So 7.68 is above both bounds, and we can see there's a longer relationship there. Let's see the next slide. So this is from table 5. You know what, let's just go to the next slide that has the whole table. So I've got trying to predict labor vote intentions. I have 3 independent variables: prime ministerial approval, economic optimism, and leader of the opposition approval. And for each one, I estimate an ADL model. And for each one, then I calculate a long run multiplier. And I get a t statistic for each one. So 7.68 for prime ministerial approval is above both bounds. The bounds are 1.01 and 3.65. They're down there in the note. So 7.68 is above both bounds, and I can safely reject the null hypothesis and say there's a long run relationship between prime ministerial approval and labor vote intentions, which goes along with lots and lots of Harold Clark's economic optimism is between the 2 bounds. Right? The economy is not a great predictor. The economy may or may not be in a long run relationship with prime ministerial, with labor vote intentions over this period of time. So it's between the 2 bounds. I don't know whether it's stationary or not stationary, and so I can't make a conclusive finding there. Leader of the opposition approval is negative and beyond both bounds. Again, the bound is 3.65. My long run multiplier is 4.93. That's above both bounds. I can safely reject the null hypothesis and say that there's a relationship there. Next. Okay, so I have 2 more quick examples that I'll go through here. Or should I stop, Carl? What do you think?
Yeah, I think maybe we can invite any questions, and as of now, we can do. If we have extra time, we can go back to these illustrations. What do you think, Peter?
So can you hear me now?
Yes, I can. Good.
Okay.
Good.
I have to apologize, Professor Lebo, because of some technical problems. I cannot jump in earlier this morning. Okay, just in terms of the questions, I have to say that some of the technical part really is over our heads. I'm here for our students, but we do have. I did collect a couple of questions. I'm not sure if it's too naive or something, but I'm still just let you know the questions here. Let's see that if the question is meaningful. And one of the questions is that what is the inconclusiveness imply? Well, we have the bound methods, right? So there's upper bound and the lower bound. So what does the inconclusiveness imply to statistical power? Or what does it mean in terms of the type 1 and type 2 errors? So this is one of the questions. And the other one is quite related too, because it says that isn't the upper bound critical value more important to conclude whether an LRM exists? And there's an inconclusive
Can you all hear? I have I think about 30 seconds I cannot hear the sound of Peter. Can everyone hear Peter's question? Matthew,
I
can you
heard
hear the
Peter's question.
question? Okay, good,
I
good.
heard Peter's question. Could you
Yeah,
hear me? I was talking there.
yeah, I can hear you. I can hear you well. Maybe it's just my ear set. Yeah,
Yeah, I can hear. So
good, good.
So I'm not sure if it came through, but I was saying this inconclusive territory, it's quite possible that findings in there are type 2 errors.
Mm-hmm.
That if we knew the true characteristics of the data, we might have narrower bounds, or we might be able to just use one critical value, reject a null hypothesis. But we're trying, this is a conservative approach that's more concerned with not making a type 1 error.
Mm-hmm. So, can you hear me?
Mm-hmm.
You know, yeah. So that could be attributed to some insufficient information, and as indeed, and related to type 2 error, or related to the some sample and in other contexts, but in time series, and particularly in this type, and we do not have all the information. So, when you have regular tests, we do that. Oh, this is above zero, below zero. Then we can make the rejection, or we cannot reject, and it's very clear cut. But identifying or finding out this inconclusive territory, and so that give a little bit more grain of salt to those clear cut situations. That, oh, we reject the hypothesis, but actually we are not sure. So that is an important part when you incorrectly reject the null hypothesis, or incorrectly accept it, and so that will be an important thing that we know we actually are not sure. Matthew,
Yes.
what do you think? What is that right?
Yeah. The especially among political scientists, political scientists often borrow methods from economics or from statistics, and sometimes our data is just not as good as the data from the disciplines that we're borrowing things from. And we grab these models very quickly and we use them. And so these models, the GCM model, has been used so many times, thousands of times, by political scientists, and so many type 1 errors, so many relationships have been found. And so that's really where I came at this project in 2016, writing about these inferential mistakes that are very easy to make. It's definitely a philosophy, right? I worry more about type 1 errors than type 2 errors. If I
yes
possible making type 2 errors, I got to work harder. I got to work harder to reject my null hypothesis. But I'd much rather be
or
there.
Get better data.
Yeah, or get better data, or longer data. There's another paper, not by me, by Mark Neiman and Dave Peterson, where they use Bayesian techniques to try and narrow the bounds. That they use, Bayesian ideas about what the possible properties of the data could be, and from that narrow the bounds. And that's got promise as well. Yeah.
Peter?
Yeah. Thank you. Yeah. And maybe another layman question about is that without the bound methods, what would be the conventional critical values usually located in between the bounds, or that's irrelevant?
Well, we wouldn't use them for long run. I guess for long run multipliers, they would be yes, between those bounds. If we could figure out the properties of the series, then we would know exactly what they were.
Mm-hmm.
Well,
So I'm still waiting for questions from students in our side on our side, but I can reflect upon your paper and also finding about the bounds and I think how much that could be attributed, for example, the way that we collect the data, and imagine that the data could be uh, could have some measurement issues, you know. So you know that we took Dr. Clark as class and we do it a lot and about how much we actually measure the variables without good precision, or maybe a lot of data coming from uh, uh, the part we actually did not measure or we think we measure, and that uncertainty part could contribute to this kind of uh, uh, false positive case, and could be one explanation. The other another thing I want to ask Dr. Lebo is that, and you study fractional co-integration, and so how that could throw more light into understanding this. If the I is not exactly what we believe is like a integer. Yeah.
So when the bounds take into account every possible combination of series, it also includes fractionally integrated series.
Mhm.
Fractional integration methods are a way that we can diagnose the series and treat each one separately, sort of a pre-whitening strategy before
Mhm.
before running a regression. We find out what the fractional integration parameter is for y and for x and for all of the x's, and then we turn them all into white noise series, and then we run a regression without
Yeah.
mixed
Mhm.
regression.
Yeah. Box change.
I did lots of work on that, and that
Yes.
you know that people are pretty resistant to doing our FEMA models, especially with short data.
Yeah. Yes.
To estimate
Mhm.
fractional integration parameters with less than 100 makes
Yeah.
makes people nervous. It's not easy to do. It's very
Mhm.
it's difficult.
Mhm. Can you go back a little bit, talk more about, because I think widening could be a different technical term or to students, and now when we first took the class on Box Jenkins time series, and that is important. Can you talk a little bit more, less technical part about what is widening and how to make white noise, and yeah.
Less okay. Well, this finding of Granger and Newbold in this 1974 paper that
Uh-huh.
any two series that have this random walk property, you're
Uh-huh.
75% likely to find a relationship between them, led to all sorts of econometricians trying to come up with solutions. Well, what should we do then to avoid those kinds of inferential mistakes?
Mm-hmm.
So the idea of pre-whitening is, okay, your data have these tendencies in them, and we're going to remove those tendencies, and we're going to deal with what's left. So
Yeah.
so if you can take, say, presidential approval, instead of looking at how presidential approval goes up and goes down over decades, you look at its changes from one month to the next. Then that's a stationary series, and that's much easier
Mm-hmm.
to
Mm-hmm.
avoid inferential mistakes. So there's, differencing is one way of doing it. Harold Clark
Yeah.
studied co-integration stuff and brought in Engel and Granger and
Yeah.
two-step and
The RSE, yeah. Mm.
yeah, and the Box Jenkins techniques were very big in the 1970s, and not many
Yeah.
people do them
Mm-hmm.
anymore. Transfer function models,
Mm-hmm.
but it's very time series is much more complicated than cross-sectional
Mm-hmm.
data. It's
Mm-hmm.
shorter. You haven't got as many observations. Exogeneity is sometimes very hard to find or prove. It can be that
Mm-hmm.
Y is causing X
Yes.
and then
Yeah.
that's possibly why there can be, you know, circularity, and it's very hard to model that stuff. So I mean, my experience has just been people try to squeeze an awful lot out of very little data, and that's led to people over claiming their findings. And so really this is a simple method, I think. It's much simpler than sort of going through all the different inferences that you would make if you were able to figure out your what your time series were. It avoids unit root testing, which is really, really a pain and often inconclusive.
Yeah. So it brings back a lot of memories when we took the time series class from Dr. Harold Clark, and it's a very thorough training, and from basic Box-Jenkins, ARIMA, and then transfer function, and then later to the London School economics approach, and Hendry and Granger, and all this, and but that is really fun. But I think you bring these studies to another level, and I think you're getting well renowned for this bring this fractionality of this I process, and so really want to invite you to give another talk on Orfema and do more and fractional too. Now let me ask. Now we have a question on our side. Instead of borrowing these models from other disciplines, are you aware of any research work on developing novel techniques from a political inferences perspective? I think it's referring to inferences. Yeah.
So the Pesseran, Shin, and Smith, those are three economists, and that their method, I borrowed it. I used it in a paper and tried to introduce to political scientists about 15 years ago, and it didn't get popular. But Andy Phillips at the University of Colorado published an AJPS 3 years ago and introduced the PSS test. But the method that I showed you here, the WLL bounds for the long run multiplier, that is novel. That's Susie Linn and Clay Webb in my work, and that's I think better suited for political data. The PSS test is suitable, or is easier to use when you have long data. It's always length of data. Political scientists don't get to use such long time series as economists do.
Yeah. 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 Andy did give a talk, and I think last year, and when he was I saw him. I met him when he was still A&M, and then he moved to Colorado Boulder, and gave this talk also, and he gave a really good roadmap on how to design and what procedures, etc. That's really good paper, and I think that you mentioned that we do not have many good long time series in political science, and do you have something like maybe a ballpark, and if you have like 155 cases in your paper versus maybe 50 cases in another IR paper, and so do we have yeah.
You know, there are political time series that can be quite long, or time series that. So, for example, in our book, we use the index of consumer sentiment, which is monthly back in 1977, and that's
just super long.
and that's 600, 700 months. And even with 600, 700 months, we can't quite figure out whether it's a unit root, because the tests just aren't powerful enough. I think it's fractionally integrated. My co-authors think maybe it's unit root. You know, I managed to find that everything's fractionally integrated, but that's a very long series. A lot of the British time series is just great. I think that's why Harold, that's part of why Harold enjoyed working on it so much. Is the British data are so long, it doesn't go through the huge well, maybe the last couple of weeks it does, but it doesn't usually go through the huge gyrations that American politics does when the presidencies change or when there's a rally around the flag effect. That can be, 200-300 months of a single party in power, or you can get monthly data. I've studied presidential approval for 600 plus months, but it's still, so there's a series might look like it's a unit root, but it could be that it's near integrated. It's almost got a 1.0, but really it's like 0.95, and it will revert back to it eventually.
So do you have a chapter on that, on a fractional time series? And
there's a little bit in the book.
Yeah. you should have one more, or maybe 2 chapters dedicated to that. Going back to David, and David is actually has an engineering background, the person who asked the question, but it's a good question, and indeed, and political science borrows a lot from other disciplines, mostly in econometrics, and now we do a lot. I think you know that we also went through some trainings from Dr. Clark, and he also borrowed and he taught a lot of methods in psychometrics too. So like SEM, and he's just so prolific in many different methods, and lane growth curve, like education, and XLM, XLM, multi-level models, and but you are really specialized in time series, and particularly in FEMA models, and well renowned of that, and when he I've been with him when working in almost the same environment with him, and talking a lot about you and Robert, and particularly you, and on time series, and we've been thinking about inviting you, and but if he is here, and it will be a really good conversation, and there would be great dialogue. So we should have invited you earlier. Yeah. All right. And sorry, and I digress too much. And Peter, do you have additional questions from our side? I also invite students. Either you want to speak up the questions or type it in the chat box. Or David, you have any follow-up questions? Please go ahead to do that.
Yeah. In terms of question, not here, but myself, I just want to add a few words, because I can see how today's talk really flashed back the memories, right? And I think it's a wonderful way to pay tribute to Dr. Harold Clark. In case some of the audience today is the first time to join us, I think this deck, this colloquium, Dr. Clark, he was in an advisory board and one of the founding person of this colloquium. And I think for the past 3, this is the 3rd time, right? This is the third talk for this series.
3rd year, yeah.
Yeah, in the 3rd year, and today, Dr. Lebo, is the third talks of this season. So we always think of Dr. Harold Clark, and so I think this is wonderful. So whatever, all the things that you've been talking about, although some of them are really over our head, technical part, but still keep hearing about Dr. Clark. I think this is, for me, it's really, really wonderful, a wonderful way to do this. I think you will be very glad we have this talk today. All right, and in terms of the questions, not for now. So is there anything there, Carl? And is there any other questions you want to bring up?
Yeah, actually, I have a few questions too myself. I wanted to see if other students have any questions. I think it's a great opportunity to ask Dr. Lebo and about this, particularly some application questions. If you have any questions about applications, or instead of just the technical part, of course, the technical part is great. And but if you have any questions about applications, how these could be applied to your research, other disciplines, and I have students from not just political science or public policy, public administration. Yeah. Then while we're waiting, I can ask some more questions, and particularly about the way that we check out the bounds. And I think as from table 2, I saw you did it quite exhaustively and doing 100,000 simulations. And so you did it. Give it a little bit more detail about this process of developing this table. This is a really high, valuable table for us to really check the inconclusiveness in such tests, and particularly important if you fall into the territory, you're actually making a wrong inference. That is important table to really attend to.
Yeah, this involved using the University of Kansas's supercomputer.
One of the students there?
You had to book, it was Clay Webb is really, he's the whiz, and he would have to book some, you book some time, you run your thing through the supercomputer, and there were so many runs. I remember in my dissertation in 1999 at North Texas, I did simulations on. I borrowed the computers of some assistant professors in the department because they were Pentium 75s and they were fast. And it would take, I think I would run like 100,000 regressions and it would take a month. So some assistant professor would have like a little icon on their computer running all the time with my dissertation simulations. But now, we ask for millions. So we want, you simulate data that has relationships in it, and then you simulate data that doesn't have relationships in it. And you simulate data of all these different possible types that could have stochastic trends or deterministic trends or random walks or stationary or autoregress, all these different things. Really, all the different things that I haven't talked about wind up being in the middle. And it's really the bounds are established by some combination of unit root and stationary on this side, of unit root and stationary on the other side. And to do that over and over again for different numbers of independent variables, different levels of significance.
Alpha.
Yeah,
and also sample sizes too. So this is really a lot of work, and then look at the table, and we take for granted. And this is just another critical value table. It's not that simple. I think it's a lot of work in there. Reminds me of some work with Dr. Clark, and we did some similar approach, and we basically do the regression and like similar to the semi machine learning approach, and we did multiple combinations and of all the independent variables in the data set. For example, would be 100 of them, to just try all the combinations, because we could be worried about like multicollinearity, and in machine learning context, we see about regularization or shrinkage. But we basically just run all different combinations, including the sample sizes. So it told me that he runs millions of models and billions of models, but using his own computer. And but the procedure is very straightforward. Stata is something as a procedure now that kind of robust. Okay, we can do that. And so next morning it came to me, I just ran 2 million models last night. Yeah, that is something similar, but not in your level. Not as, and in your case, it's much more work because it takes more different combinations. We just look at a combination of different independent variables. Yeah. So do you expect this could be something we can even look forward to more applications or checking into the future and how much you think you can expand it to other but particularly looking at the bounds and looking at this gray zones and how much we can extend it to future research or the more new genre of time series models and yeah, what's the next step? Yeah.
I in an introductory class for time series, you can be able to do this after, just a few weeks. So when I teach time series now, I used to teach time series and it would have 4 or 5 weeks at the beginning on box Jenkins and transfer functions. And now I don't teach that anymore. Now I teach, I start with stationarity and testing, and then very quickly get into co-integration and bounds tests. So we're teaching, this is being taught now at ICPSR, and it's being taught at a few different places. It's being used more. It should be more accessible. It should be, I hope that it's used a lot, but the temptation is that people don't like a method that is conservative. They like a method that shows them, oh, wow, that's a very significant result. And so it's
I like the stars.
Trying to get people to be more cautious is not an easy selling point.
Yeah. Now David is back, and now I think he's showing his engineering background now. While on the topic of time series analysis, I would like to throw out our current one. I know there's a new analyzer used in the mass spectrometry, like a spectral analysis, that uses a Fourier series. And is there such an application for Fourier series in political analysis?
I don't know.
Yeah,
I don't know.
I cannot claim that expertise in that direction too. And but I think there should be some similar ways of tackling problems through simulation. And but you have different mathematical problems, we still can try simulations to do something we cannot really theoretically derive, mathematically or theoretically derive. We tried simulations. Yeah.
I think that there's somebody who's done spectral analysis in political science. A guy at a Portuguese university has done some of that.
Yeah.
A little bit.
Yeah. I hope maybe in future we can answer a question, David. Yeah. That's good. Now let's see. Do we have more questions? And I know it's getting late in Canada, and let me see. Peter, how's your side?
No more questions here.
Okay, so I think I will wrap up here, and I'm a little bit early, and actually it's not too early. And thank you for joining us for this data analytics colloquium. And all the materials and the video will be uploaded to the website dacolloquium.com. And our next talk will be by Dr. Christopher Aiken, and but he will be giving a talk on 27. And please check our website and the latest talk on his talk on multinomial probit, and also more generally the scaling, what kind of rescaling problem for this kind of nonlinear probability models. And the time is a little bit different. And Peter, please confirm on that. Because of, again, want to change it to an earlier time to accommodate the East Coast speakers. Yeah. Okay, I think if we do not have further questions, I want to give a round of applause to our speaker, Dr. Lebo, and I wish we can more time to chat, catch up, particularly the old time, and we look forward to inviting you back Dr. Lebo, and I think there are a few more topics we can talk about, particularly RFEMA and fractional integration, etc. Yeah. Thank you again.
Thank you so much.
Yeah, yeah. All right, and I
Thanks.
probably should let you exit because this is quite late. It's almost midnight now, and right?
Yep.
Yeah. And
Thank you so
no,
much.
sometimes, yeah. Thank you,
Thank you for inviting
Matthew.
me. This was really a treat, and to think about Harold too, and see more of his students.
Yes, and
Thanks.
we look forward to actually more events like this, and yeah, maybe sometime we should talk too, and to see whether we can get together maybe in the next conference, maybe Midwest or APSA or maybe in a Canadian conference, etc. Yeah.
Great.
All right. Yeah.
Right.
All right.
And
Thank
yeah,
you.
audience, please don't forget to come back for Dr. Aiken's talk. Thank you all for coming today.
All right. Okay.
Yeah,
Thanks.
Dr. Lebo. Yeah.
Good night. Good morning.
Okay. Good night. Good night. Good night, Matthew. Okay. See you soon, and we cross paths soon. Okay. Bye.
Bye.
All right, and